Alright, so let's start with the doubt sheets. So there is a student who has misheard and heard the complete opposite of what I said. They said, sir, you said that we will be dealing with convex functions only. The other way, right? We will not be dealing with only convex functions. We will be dealing with functions in general. They may be convex, they may not be convex. Now, do we need to check whether the optimization function is convex before solving the problem for exams and assignments? I don't think you should make any assumptions whether the function is convex or not. So, for convex functions, a local minima is a global minima, but are majority of the objective functions convex? If not, is finding a local minima sufficient? So we discussed this in the previous class, right, that for convex functions a local minima is a global minima. So if you have found a minima, that's it, your search is over. But that said, I would say that most real life engineering problems are not convex. Okay, people try really hard to somehow make a convex approximation of their problem, and the reason is simple. Once you do that, you just need to find one solution. So this, right in the beginning of the course, we had spoken about complexity of modeling the problem versus how simple is it to solve the problem. So if you make it really simple and make it convex and solve it, then you have to see how realistic is that model, right? So it's never an easy answer. Could you share some open research problems and papers on choosing the initial points and the other things? So before we get to research problems and papers, let us go clear our textbook material first, right? Which is what we are doing now. Can we also have a lecture on semi-definite programming on the formalism and methods? So semi-definite programming is a very nice technique. I hope that towards the end of the semester we'll have some space for this. Okay. Could you explain the geometric meaning of continuity of Hessian? I think we spoke about this briefly last time. The Hessian has the Hessian has all second order mixed partial derivatives inside it. So whatever idea you have of continuity, you apply to each one of those guys. I can't think of any special geometric meaning of continuity of Hessian. Geometric interpretation of Hessian is there, that it talks about whether the bowl is upward opening, downward opening, saddle point, or none of these. That is the geometric interpretation of Hessian. But continuity of Hessian, I don't think there's anything special. Okay, so I'm happy that there are some simple questions being asked, because if this is the doubt, then it's better to get it clarified. So let me put the question to the class. So x belongs to Rn, okay, and if I write a function like this, this is the optimization problem. Is it unconstrained or is it constrained? This is clearly unconstrained. What would make it constrained? Right, so I could either write it like this, such that x belongs to some set, or the simpler way is just to, you get rid of this and you write, it conveys the same thing. So here you can see it's constrained because x is not free to live anywhere, it is forced to be in some set omega, capital Omega, okay, and this is a very general way of writing it. You can have also now variations of this. You could have, for example, minimum like this and x such that g of x is, I don't know, belongs to some set. So this is also a type of constrained optimization, that you're now saying the function of the optimization variable is constrained. So there are all sorts of flavors available. Okay. Is quasi-Newton method faster than Newton, and if so, what is the rate of convergence? So we will look at Newton and quasi-Newton algorithms in detail as we go. Newton is as fast as it gets with quadratic. Quasi-Newton obviously will not be as fast, but it gets close. Which direction is considered good in the case of non-convex function? What is actually meant by stuck at a local minima? Okay, so these are things that we will spend a lot of time talking about. But again, this is a basic question, so let me clarify it. What is it meant by saying being stuck in a local minima? It just means that if let's say I start my optimization from here, I'm over here, and at this point I ask, should I go up or down if I want to get to a minima of the function? Obviously the answer is, to go down I have to take a step to the right. So if I start walking over here and I come over here, now any move in this direction or in this direction from this point will increase the function value, so I will not take it. Right? Now if this function on the other hand happened to be something like this, then once I've reached here, I will never get out of here. Even though the true solution is here, I will not, there is no mechanism for me in the way that we have spoken about so far for us to get there. So this, you would then say that the algorithm is now stuck in a local minima. Okay. And remember, I'm showing you a one-dimensional plot. Imagine this in 1 million dimensions. You cannot plot diagrams and see where you are. Okay. So that's the intuition of being stuck in a local minima. Is there something similar to Hessian for a function defined from Rn to Rm? So you could always define a Hessian for each of the output function values. Right? It's a mess to keep track of it, but that's how you have to do it. Okay, here is a question that deals with revision of your linear algebra. Does positive definiteness always infer invertibility of Hessian? So let's take it step by step. We wrote the Newton direction. Can someone remind me what the Newton direction was? Minus, right? Grad f. This was the definition of the Newton direction, which we will derive. You don't have to remember it, right? Now this and we said that the Hessian should be positive definite. We just stated it, we are yet to prove it. And the question is that, remember I made a statement that the Hessian should be positive definite, but the question is, does positive definiteness always imply invertibility of the Hessian? That's the question. Is it enough for me to say that the Hessian is positive definite for this guy over here, right? For this guy over here to exist? Is that a yes, no, or depends? Because? Okay, so the explanation from linear algebra is correct, that if this is positive definite, implies that all the eigenvalues lambda i's are strictly greater than 0. And remember, for a positive definite matrix, how did I write the eigen decomposition of the matrix? Can I write this Hessian in terms of the product of 3 matrices? What was it? V eigen decomposition, not singular decomposition. So let's use the standard symbol. Let's say Q. Next would be capital lambda. Next would be, are you sure? So there is a transpose that we have to get correct over here. Let's assume it's real value. So if I put the transpose over here, right? So this is correct. Now, what was the property of Q? What was in the columns of Q? Eigenvectors. And what is the property of eigenvectors? They are all orthogonal, right? That means each of these, so therefore if all the columns are orthogonal, that means it's full rank and invertible. That means Q is invertible, obviously Q transpose is invertible. Eigenvalues are positive, therefore this guy is a diagonal matrix with lambda i's over here. A diagonal matrix with greater than 0 entries can trivially be inverted. So if it's enough for me to say that the Hessian is positive definite, because now you look at this expression, I can take inverse on both sides, it is guaranteed to exist. Which is why we said positive definite, not positive semi-definite. Because if positive semi-definite, one eigenvalue being 0 means I cannot invert it. Right? So that is the requirement. Is this fine? Okay. Alright, so we've been talking about descent directions. I think we have just stated the descent directions, I mean the property of the descent directions, right? What is the first property? Oops. Did we state it? I think that was the second property. What would be the first property? It's the direction, the steepest descent direction is, the steepest descent direction is minus grad f. I'm going to put a k here. The moment I put a k here, you know what that means, right? It means grad f evaluated at xk. So the shorthand notation is this. Okay, shorthand. So let's have a look at the proof for this, which is very simple. What is the scene? We are at xk. Okay, I'm standing over here. Now here is some direction pk, and I want to go some direction alpha or something towards pk, right? So the first thing that we could do is look at our Taylor's first order expansion, right? So f of xk plus, so instead of going the entire length alpha, let's just go some small distance epsilon, so that our use of first order Taylor's theorem is accurate. I can make epsilon as small as I want, so that my first order approximation is correct. Okay. First term is going to be f of xk, simple. Second term is going to be, there's going to be epsilon. Next is going to be grad f at which point? Xk, right? Transpose multiplied by pk, right? The epsilon is already taken out. There is an error in this approximation to the order of what in epsilon? Order of epsilon squared error is going to be there, which in the first order Taylor theorem we ignore. We say, okay, there is an epsilon squared error, which is, so that's why we need to take epsilon small. If epsilon is, for example, 10 to the minus 5, the error is of order 10 to the minus 10, so I can ignore it. On the other hand, if epsilon becomes 10, the error is 100, right? That's the intuition for taking small epsilon. Okay, now let's look at this term over here. So the expansion of A transpose B or X transpose Y, how have we been doing it algebraically? Multiplying each of the components, x1, y1 plus x2, y2, right? That is the algebraic picture. What is the geometric picture? It's an inner product of two vectors in n dimensional space. Okay, we cannot visualize it, but there are still two vectors in n dimensions. And two vectors in n dimensions, we can also define an angle between these two vectors in n dimensions, right? So we need not be limited by our imagination. So just extending that generalization, we would write this as norm of, right, first term. Second term would be norm of pk. Third term would be cosine of the angle between them, right? So I can just very simply think of this as grad fk, this is my angle pk, and this is my angle theta k. Okay, very good. Can we say anything about the sign of this quantity? Norm of grad fk has to be positive or greater than equal to 0, because it's a norm, quite obviously. Similarly, this term will also be greater than equal to 0, right? So remember where we are at. We are at some point xk, we are wanting to go to xk plus 1, and we want to test, we want some simple test to tell whether or not it's a descent direction. Descent direction, in plain and simple words, what should be the effect of going in a descent direction? The value of fk plus 1 should be less than f of k. That's the logical meaning of descent directions. That means this guy over here has to be less than this guy, right? So let's just note it down. fk plus 1 should be less than fk. If this is to be the case, what does it imply? Let's ignore this error term. Let's look at this guy over here. What does it imply for this box term? Has to be negative. That's the only way it could be a descent direction. So implies that grad fk transpose pk should be less than 0. Now we have opened up this expression over here. It has two positive terms and one term which can flip sign. Cos can be positive or negative. So therefore, if I wanted to have maximum decrease in the function value, if it were in your hand to choose p, right? P is what is in your hand that you're trying to figure out. What would you choose? What value should you pick for theta k? Pi, 180 degrees, right? Because if this angle is like this over here, then the inner product is going to give me a -1. That's the maximum I can reduce this value, right? So maximum decrease in f happens when theta k equal to pi, right? So very simple result that is coming just by plain geometry. So therefore, what is this when theta k equal to pi? What do we call? That's why it is called. So implies pk is equal to what? Simply negative of grad fk, and that's why the word has come for it. Direction of steepest descent. This is the direction in which the descent is the steepest. So this is how the word steepest came into play. Right. The other word given for this direction is gradient descent. How do we parse that? You have this is gradient and the minus sign here, this is descent. So technically they should call it descent gradient, but okay. So that's why these two are the equivalent descriptions of the steepest descent or gradient descent. Don't get confused between the two, they mean the same, right? Any questions on this very simple geometry? That's all there is to it, you know, and large parts of machine learning are built on just this algorithm where I don't have to cook up a direction each time. Calculate the gradient of the function, put a minus sign, you've got your direction in which to go. It will work as long as what? What is the, keep the approximation in mind. This will work as long as epsilon is small, right? If epsilon is small, this is always going to work. Why? Because the error term is epsilon squared, even larger. But as you start get greedier and greedier, you want to make epsilon larger, this approximation may not be valid, right? The error term may dominate your approximation. So keep that in mind. Okay. This also this picture that we have over here, right? This picture over here also gives us a more relaxed way of thinking of a descent direction. What do I need for descent then? What should be the condition on theta k? Do I have to choose theta k equal to pi, or can I choose some other number? Exactly, theta k, as long as, right, as long as pk is here, pk is, right, so let's say this is my pk. This is all right, because pk dot grad fk, this angle over here, will always give me cosine of that is less than this. Therefore, xk plus 1, f of xk plus 1 will always be less than f of k. So this gives us a little bit more breathing room to say that, okay, I can choose this theta k to be any angle greater than 90 and less than minus 90, right? I can also go from here, right? The simpler way of saying it is, right, so if this direction therefore is minus grad fk, so you say that a direction, let's write it down now, it's quite straightforward. A descent direction makes an angle belonging to minus pi by 2 to pi by 2 with minus grad fk, right. So, this gives me actually freedom to come up with different algorithms, different ways of descending. One of the prime examples that we will talk about in some time in this course is what is called the conjugate gradient method, which does not choose steepest descent. It chooses a more clever direction and gives us a faster convergence than gradient descent, which we will talk about. Okay, this is fine.